Hey guys, welcome back to another lesson video where today we're going to be talking about quadratic equations, which is mostly a review from Algebra 2. Okay, so our objectives for today, we're going to solve equations by using the zero product property, solve equations by using the square root property, we're going to complete the square, solve quadratic equations by using the quadratic formula, use the discriminant, and solve an equation for a specified variable. So again, a lot of just review from Algebra 2. So we have a quick definition here. So let A, B, and C represent real numbers where A can't be 0. That makes sense because if A is 0, you don't have a quadratic. A quadratic equation in the variable x. The reason why we state that is because that's the variable in the form. But you can use any variable you want. It's just x is one of the most commonly used variables, and it's seen in a lot of definitions. So is the equation in the form ax squared plus bx plus c equals 0? And this is a second degree equation. Okay, so something just to keep in mind. What we've done in the past was primarily first degree equations where the variable has a 1 as an exponent. This is a second degree equation. And the way we classify these equations is by looking at the largest exponent. So even though we have a variable here with a 1, that's still not the largest. We look to this guy, and that's the largest, which is 2. That's what we call a second degree variable. Let's look at the zero product property. If we have m times n equals 0, then m equals 0 or n equals 0, okay? Which makes sense. If this is 0, multiplied by n, I get 0. If this is 0, multiplied by n to get 0 there, okay? So it has to be one of these to give us that result. I want to put up here caution. It's not true for any other number other than 0. So for example, if it was m times n equals 10, it's not m equals 10, n equals 10. Okay, that just sounds weird, but that's just not the case, right? This is not a true statement because here's the deal. If this was 10, this has to be 1. If that was 10, that has to be 1. It's not saying that it has to be both of these being 10. Over here, both these could be 0, and that still works out. So yeah, and again, I don't think it's something that you guys really need to worry about. I think you guys are okay with it, but I think it's worth just emphasizing. Here's an example. So we're going to solve the equation using the zero product property. Okay. So our first example, we have x squared minus 16x equals 0. Our second example, 3x minus 4 equals negative 3. Looking at the first example, notice that my constant term's gone. And when that happens, typically we can maybe factor a GCF out, okay? So let's do that. Now this looks like our definition, okay? These two multiplied together gives me 0. Therefore, I can go ahead and set each one equal to 0 and solve. The first one, I don't have to solve. It's already solved, it's 0. The second one, it's a one-step equation. I can just add 16 and I'm done. So my solution set, we'll put the little nice curly brackets out, is 0, 16. That's my final answer. Now for part B, it's not equal to 0. That's an issue. So what I'm going to do first, I'm going to go ahead and multiply these together. Add the 3 over here, then it's equal to 0. Then I can probably use this to solve for x. So when I multiply these, I get 9x squared minus 12x plus 3 equals 0. I'm distributing and adding the 3 over in one step. This is not looking like this yet. What that's telling me is maybe I could factor this to where it looks like this, because now it is equal to 0. I just have to factor. And with those numbers, they're not that large, but it might behoove me just to factor a GCF out. So let's factor a 3. So we get 3x squared minus 4x plus 1 equals 0. Okay, now those numbers are a little bit easier to factor, and they do factor out nicely. One of the things I mentioned in class was this. You can go through the process I taught you in Algebra 2 in terms of factoring, but we can guess and check and get to that answer possibly a little faster. I know that the outside has to be a 3x and an x, because when I multiply them, I get 3x squared. I know that already. Now, the last numbers have to give me a 1. Okay, well there's two options. I can have a positive 1 for both, because it gives me a positive 1 when I multiply, or a negative 1 to both, which when I multiply I still get positive 1. Well, if I put a plus 1 here, okay, and I were to multiply both of these, am I ever going to get a negative 4x? And the answer is no, it's not going to happen. So if I put subtraction there, now it can happen. And just some quick mental math, this gives me a 3x squared. This times this gives me the plus 1. Perfect. Let's look at the middle term. 3x and a negative 1, negative 3x. Negative 1 times x, negative x. Combine them, negative 4x. We're good, okay? Not too much time is spent on that because the factors are smaller enough to where we can do it. Up here it might not be as clear as to what those factors are, but making them smaller, we can get there sooner. We'll set everything equal to 0, every factor. Notice that one of the factors is, well, a contradiction. We know that that's not going to equal 0. And do you have to write that every time you see something? No, not at all. It's just our example in the notes. I want to make sure you understand that. I'll add 1, divide by 3. So x could be a third. Add 1 over here, x could be a 1. So our two solutions, 1/3 and 1. There's my solution set. Not too bad, huh? Okay, let's continue. Another little definition. The square root property. Okay. I am infamous for capitalizing things that don't need capitalized, so I apologize to all the English fans out there. I try my best with it. But my brain's just so used to writing lower and uppercase like mixed in like that, it's hard to break. And yeah, I'll change the lowercase there. But I'm trying my best with it, like I said. If x squared equals k, then that means x is equal to positive or negative square root of k. Again, we've seen that before. We're just trying to establish a definition with it. This tells me that the solution set is negative square root of k and positive square root of k. Or, we can write this more concisely. We can combine them into one and saying that is just positive negative square root of k. Either list them or combine them with the symbol. Both are acceptable. Let's try an example out. So again, we're just going to solve the equation using the square root property. There's my two examples. And if you're watching this, I would encourage you just to pause the video and try them out yourself and then see how I do it. But if you want to follow along, nothing wrong with that. There's no linear term, so therefore I'm not thinking like quadratic formula or complete the square. Immediately I'm thinking maybe I could solve for w just normal like algebraic methods. I'm going to subtract 40 to the other side. Divide by 5. Again, trying to get the variable by itself. Okay. I get w squared equals negative 8. Typically, we don't like stuff that's negative under the square root, but we know how to manage that now. We know how to work with complex numbers and imaginary numbers. W equals to positive or negative, square root of negative 8. We can take the excuse me, we can take the I out, and we can break down square root of 8. Excuse me. Oh. Next, that becomes a 2. We'll put I next to it, and then square root of 2 comes after. Again, we use the little curly brackets. Then our solution set is plus or minus 2i squared root of 2. Now over here, this is what we're going to talk about when we do complete the square, because this is our goal with complete the square. Can we create something like this? Because from this step, it's easier to solve for the variable. I want to get rid of the exponent by taking the square root to both sides. Y plus 10 equals positive negative square root of 27. We'll subtract the 10. And we're pretty much done. It was that simple. So you can see why this is such a benefit, especially to math people who are like, well, if this was easy to write it or to find the answer in this format, maybe we can use that process to actually create this for any quadratic, and we can. Still break down the square root of 27, that's 9 and 3. So that gives me negative 10 plus or minus 3 square roots of 3. And then we'll just put in the brackets. Man, I'm having a hard time writing today. There we go. So our solution set is as follows. That's a square root property. So the next thing we're going to talk about is complete the square, but before we do that, I have to mention how to create what's called a perfect square trinomial. We need to know how to do this before we complete the square. So just a little recall. Okay. To create a perfect square trinomial, we square 1/2 the linear term, then add it. Okay. It's always good to have an example with it, right? For example, if I had this guy, x squared plus 10x, what can I add to it to make it a perfect square trinomial? Well, let's back up real quick. If I had this equation here, this equation is a perfect square trinomial. How do I know that? Well, what factors of 64, when added, gives me 16? It's 8 and 8. And you're going to see it twice. That's the characteristic of a perfect square trinomial. You're seeing the same factor appear twice. Therefore, I can condense it with an exponent, which eventually will get me to this guy over here, what this looks like. Okay? So how do I create that? Well, it's pretty simple. What you do is you take half of this guy, which is 5. Then you square it, which gives me 25. Now, does this lead to this? Yes. Factors of 25 that add to give me 10, 5 and 5. This is x plus 5, which becomes x plus 5 squared. So we get what we want out of the trinomial there. Okay? So we're going to use that process to help complete the square. So let's try a couple of these out. Okay? So we're going to find n that will make the polynomial a perfect square trinomial. Then factor the result. just like what I did up there. Okay, I got two examples. So for A, we have x squared plus 7x. For part B, I have x squared plus 5 over 4x. So in other words, what I want to do is I want to figure out what do I plug in for n that makes it a perfect square trinomial, which gives me to that result, where it's the same factor twice where I can combine it. Well, if you need to, and it's okay if it comes out to be a fraction. I know people freak out with fractions. You didn't do nothing wrong. I know I have to take half my linear term, so 7 over 2. Then I got to square it. Well, that becomes 49 over 4. Don't work with decimals, because if you work with decimals, it's not going to help you to factor it or to solve for x, okay? Leave it like a fraction, it's okay. So this is our n value. Now, if I rewrite this, I'm going to erase this for a second. So this is 49 over 4. Now, if I want to factor this, I know it has a fraction at the end, but what two factors of this guy add to give you 7x? Well, you found them already. Okay, look at this example, which is a little bit cleaner. Okay, what were factors of 25 that added 10? It was 5 and 5, which was half your linear term, right? Go over here, factors of 64 that add to 16. It was 8 and 8, half your linear term. That's a characteristic of that perfect square trinomial. So what's half of this? Well, just 7 over 2. So this factors to x plus 7 over 2 squared. Again, you can go ahead and multiply this out to see that it does work. Because think about it. If I add this together, I get 14 over 2, which gives me 7. Perfect. That's what I wanted. Okay. Now over here, same thing. I'm going to take half of this guy. So I'm going to multiply by half instead so you can see it a little bit better. Then square it. So this would be 5 over 8, which gives me 25 over 64. Okay, so that's n. Not clearly an ideal number we want to work with, but that's okay. Now, what are factors of this that add to this guy? Well, just like before, it's half your linear term. It's 5 over 8. So this is just x plus 5 over 8 squared. Okay. What do you think? Not too bad, right? It's tough talking to a camera with no students to shake their head up and down or left to right. I don't know. But hopefully that makes sense to you. Now that we have that under our belt, we can start completing the square. Now, just to point this out there, because we can manipulate any quadratic like this, we can manipulate it to where we create this perfect square trinomial. You can complete the square to solve for any variable in a quadratic. It will always work, okay? If you remember from last year in Algebra 2, we used it to derive the quadratic formula, because it always works. So just keep that in mind. At the end of the day, complete the square if you're not sure how to solve it. Complete the square process. Okay? If you like to write down steps, perfect time to write them down if you're that person who needs them. First step, divide both sides by a to make the leading coefficient 1. Assuming if a is not already 1, okay? I'm also going to abbreviate in the future, like future videos and stuff, I'll abbreviate it as LC, leading coefficient. Step 2, isolate the variables, meaning variables on one side, numbers on the other side. Step 3, complete the square. I'm going to cheat and just abbreviate. Let's complete the square by creating a perfect square trinomial. Okay. Then add the term to both sides of the equation. Which makes sense. I can't just create this by adding it to the left-hand side or right-hand side, whatever you start with, and not do it across the equal sign. It keeps things unbalanced, and then you don't have the original equation anymore. It loses its value. 4. Factor the perfect square trinomial. And then the last one, solve using the square root property. Okay, there we go. We're going to try 2 examples out. One example that's pretty straightforward, and one that has a fraction in it. That way you know how to approach it, how to solve it. Because at the end of the day, fractions aren't that scary. They don't bite. Honest, they don't bite. Example. Solve by completing the square. There we go. Okay, what do we do first? We'll look at what the steps say over there. Okay, divide by A to make the leading coefficient 1. Leading coefficient's already 1. Skip it. Step 2, isolate the variable terms. Let's move the 8x over, and we'll move the 5 over there. So x squared plus 8x equals 5. There we go. Step 3, complete the square by creating a perfect square trinomial. Once we do, we must add it to both sides. You don't have to put underlines there. I'm doing that for emphasis. So remember what we did. We took this guy, took half of it, half your linear term, that's 4. Squaring it gives me 16. Do that to both sides, keep it balanced. If you need to in your notes, put a little side thing here saying, how did you get to that point? Now, factor this guy next. This factors a 16 that give me 8, 4 and 4. We know that's going to appear twice, therefore we have the exponent to condense it, just like we see in the last example. And then add these together, we get 21. Now we're just going to solve by square root property. X plus 4 equals positive negative square root of 21. X is equal to negative 4 plus or minus square root of 21. Square root of 21 you cannot reduce any further, so we're done with that. We can use the brackets. Our solution set are those 2 answers. Now, I do want to point out something to you, okay? Because this has 2 answers, think about quadratics for a moment. Think about parabolas and the graphs. We find solutions when it hits the x-axis. I'll draw a picture. Okay, right here and here. That's where our functions or y values are 0, okay? So it comes down to this. If it hits it twice, 2 solutions. If it hits it once, 1 solution. If it doesn't hit it at all, no solutions. And we talked about that in the complex number video, how visually this has no answers, it has complex answers. So in this case, the graph crosses the x-axis twice. Always keep in mind what the visual is, because at the end of the day you can graph this and look to see if you're right. Are you going to be able to graph to see where those are? No, that's a little bit too fine print with the decimals. But you know it has to hit the graph twice, or hit the x-axis twice, and if you graph it and it doesn't, you're in some trouble. let's try, I'm going to go ahead and erase this because I want to keep this up here as a reference. Let's try one with fractions. Same instructions, solve by completing the square. Notice that A, the quadratic term, is not 1. Now, why is it so important for that to be 1? Well, think about it. When we had something like this, we were able to condense it with an exponent. When we have something like this, well, I can't condense it with an exponent. This is causing factoring to work like that, where one of the values is not going to match. Actually, let me just change it to -1 so you can see. So, as you can tell, it's not going to be a one-to-one match with it. Therefore, I can't do the rest of the process. So by dividing everything by the LC, which, by the way, is not changing the equation, okay, because everything's being divided by it, I can at least ensure myself that I'm going to get that nice result up here. So I get p squared plus 2p minus 90 over 7 equals 0. Again, group the variables like we did before, just like that. It's okay to have a fraction there, right? We know how to work with them now. Take half your linear term, which is 1, square it is 1. Isn't that nice? Over here you get a 1, okay? Factor this side, it's just half the linear term, so it'll be p plus 1 squared. On this side, I'm going to go ahead and combine them into one fraction before I take the square root. So I get p plus 1 squared equals 97 over 7. Take the square root. P plus 1 equals positive negative, square root of 97. Let's split them up real quick. Over square root of 7. Reason why I'm doing that, you'll see in a moment. So p must equal -1 plus or minus square root of 97 over square root of 7. You can't have this in the denominator, we need to rationalize it. And just to emphasize why you can't, it's not a bad thing, it really isn't. A good way of thinking of it is square root of 7 goes on forever, it doesn't end. So when you think of fractions, fractions are definite things, like 1/4 is 1 out of 4 pieces. Well, can I take something out of something that doesn't end? It doesn't quite work out. So we rationalize to help with that problem, okay? So we have p equals -1 plus or minus. So it'd be square root of 97 over square root of 7. We're going to rationalize it. So -1 plus or minus, and I think it's 679 over 7, okay? And what I'm going to do, I'm going to go ahead and just put the brackets there. I'm going to skip the step of rewriting it twice. 679 cannot be reduced, so you're good to go. All right, there's completing the square. We got one more thing to do, and that's quadratic formula. Let's take a look at those. So, quick definition. This is something that is well known in high schools. For the quadratic equation of the form ax squared plus bx plus c equals 0, where a can't be 0 because, again, it would be a quadratic, the solutions are as follows. Okay. So there's our quadratic formula. Now, where does this come from? This is a throwback to Algebra 2, because we did this in Algebra 2. But you're going to practice again and derive it. Here's the general format of a quadratic. if you complete the square with this, you get this formula. Okay, so again, something that I want you guys to try out tonight and see if you can't do that for me. So here's our first example with it. Well, our only example, I should say, with it. This is one of those things where I think you guys are okay with using quadratic formula. This, though, has fractions. I know, don't hate me with fractions, please don't. But I don't want to put that, I don't want to put these values into there. I'm a math person. I wouldn't want to do that, okay? I wouldn't expect you to do that. But we can be smart about this. Look at the denominators, 18, 9, and 18. If you recall, we were able to get rid of them, I think it was our very first lesson, by multiplying by an LCD. So what's the LCD of 18, 9, and 18? 18. So I'm going to put that over here. I'm going to multiply by the LCD of 18. Therefore, no fractions. Don't have to worry about it. So let's go ahead and do that. So we're going to multiply this by 18 and the 0, which doesn't change nothing, but I still want to show that we're doing this process to both sides. These 18s reduce out. I just get a 5x squared. The 18 and 9 reduces to 2, so that gives me a minus 8x. 18 and 1/18 is a 1, and on the other side we get is a 0. If you're that kind of person who likes to have these written ahead of time, go ahead and establish what A, B, and C are. A is always the quadratic term, the coefficient in front. B is the linear coefficient, and C is the constant. So now what I'm going to do is take these three values and plug them into the formula. So the negative 8 becomes a positive 8. Underneath the radical, negative 8 squared, 4 times 5 times 1, and all over 2 times 5. I don't know if that's comforting, seeing something that you've worked with for so long. It's nice to have something that isn't familiar territory, isn't it? It really is. Okay, so we get 8 plus or minus. That's a 64, okay? And that's going to be a 20. So this is a 44 then. I'm going to break up the 44 into 4 and 11. Okay. And I'm out of space, so we're going to put the rest over here. I know what you're thinking. Shouldn't you use another whiteboard? I would, but when I expand this back, it's kind of hard to see with my writing, and I don't want you to squint to see the video, to see the print. So down there we'll have 8 plus or minus, it'd be 2 squared is 11 over 10. And then if you notice 8, 2, and 10 have a factor of 2 in common. I'll write this out so you can see what's going on. Okay, so I went ahead and factored a 2 out of the numerator denominator. It reduces out. I get 4 plus or minus square root of 11 over 5. Okay, and in fact, what I'll do is I'll go ahead and put the brackets and make it a solution set. Okay. All right, we're doing good. Now, one thing I want to note is this guy here. This determines how many solutions I have in the type. Okay, and it has this very special name, if you remember. It's called the discriminant. Okay, so the discriminant is identified as b squared minus 4ac its value tells us the number and type of solutions to an equation. So for instance, if we have something that's negative under the square root, we know we got i's. So we're going to have 2 non-real solutions. I'm going to abbreviate solutions, by the way. If it's exactly 0, well, square root of 0 is 0, so there's nothing you're adding or subtracting to. Therefore, you have just one real solution. And then the last one, if it's positive, then you're going to have two real solutions, which we've seen in our prior examples. Now think about it in terms of graphs. If it's two non-real, then it's not hitting the x-axis. If it's one real, it's hitting the x-axis once, and two real, that parabola's hitting the x-axis twice. Okay? So we're going to look at just one example with it. Let's say I had, okay, that little quadratic. Well, first, make it equal to 0, or else we can't use the discriminant. Now, if you want to establish what each thing is, we can. All right. So b squared minus 4ac, okay, that's going to equal to negative 4 squared, 4 times a times c. So if you notice, that gives me a 16. Odd number of negatives, so it's going to be negative to begin with. Another 16, so that means a 0. Therefore, we have one real solution. Okay? All right, we got one more thing to do. I promise we're finished. I promise you. We got to solve for an unspecified variable. Okay? So they're kind of like the literal equations. So for the first one, we're going to solve for r. And a little note, r has to be greater than 0. Meaning they want a positive r value. Okay? And this right here, that circle with a line through it, if you remember from geometry, that means theta. That's the angle that it represents. This is a formula for area of a sector. And in the trig class, which is next semester, we'll talk about that more in detail. So if I want to solve for r, let's get rid of the fraction. I'm going to multiply both sides by 2. So this is 2a equals r squared theta. Now theta is being multiplied to r squared, so I'm going to divide by it. Those cancel. So 2a over theta equals r squared. And then our last step, take the square root. So for my final answer, I get 2a over theta equals r. Now I'm going to put a note. Okay? There is no negative square root because r is positive. That symbol means because. I'm just trying to do a little shorthand. Okay? So typically we have a positive negative when we do the square root, but they want the raise to be positive, which makes sense. You're talking about area of a sector. You know, you don't want to have a negative radius. That's not going to work out too well for you. All right. Last example. Okay. We're going to solve for d. Now, this one's a little different because there's no x's there. We're so used to using quadratic formula with x's, it's a little hard to wrap our minds around it. But d is just the x value. D is representing the quadratic and linear term. So pretend those are x's here. I still want to set it equal to 0 first. Then we can start deciding what we want to do. And for right now, I can't factor because these aren't the same variables there. But what I can do is I can use quadratic formula to represent what the answers could be. I can't go any further with it, unfortunately, but I can at least set up the quadratic formula, and then someone can tell me what these variables represent, what numbers. So this is my a, b, and c value. So my a is w, my b is m, and my c is, well, negative t. So instead of putting x equals, it's going to be d equals, because that's the variable we're trying to solve for. So it's negative b plus or minus the square root of b squared minus 4 times my a times my c all over 2 times my a. I know, it messes with your head a little bit because you're so used to, inputting numbers in here and not just letters for letters. It is a little odd at first. Now again, this seems like a mess, but I don't have much to do except this part. These are two negatives, so I can make that a plus sign. And then I'm done. I, unfortunately, cannot do anything else until they tell me what these variables stand for. So that's as far as we can go in terms of solving for D. Okay? All right. Well, what do you think? Not too bad. So Quadratics, this lesson was just a good little review of what we've done in the past. Hopefully that kind of refreshes your mind with that information. Little new stuff, not a lot of new stuff, but like what happens if we have a little restriction? We just get rid of the negative component. Or what happens if we have all variables? Well, we can get to this point, but unfortunately we can't solve it. So, but anyway, hope you guys are doing well, and hey, I'll see you in the next lesson video. Take care.